So as a final look at this, we're going to actually use centered rectangles. And they're called centered rectangles because the height of each rectangle is at the center. So what we need to know here is f of 1.5, f of 2.5, and f of 3.5. This is potentially another answer to the last example as well. Centered rectangles ought to be better. I'm sure we could construct situations where they're not, but in general. So 1.5 cubed, add 1. So that's going to give me, I'm just going to go to decimal actually. So let's just change that one into decimal. 4.375. And f of 2.5, so 2.5, that's 25. 2.5 cubed, add 1. 16.625. And 3.5. 3.5 cubed, add 1. 43.875. And so we want to just add those up, because remember all the widths were 1. And that gives us 64.875. We should always state square units. And the true area, which can be found by integration, and we're going to come on to that slightly later, is 66.75 square units. So we had the 39 with the left rectangles, we had the 102 with the right ones, and the center ones gave us 64.875. Just as a matter of interest, what happens when we average those two? So we've got 39, add 102, and if we divide that by 2, that's 70.5. So it's not as good as the centered rectangles, but certainly better than either of the individuals if we compare it to the true area. While we're on this, I mentioned about more rectangles. So I've got the situation of the left rectangles that we used before, and the area is 39 actually. I'll just move that in the shot here. Area is 39. So it's a lot of computation if you do it manually, but let's just use a lot more rectangles. So let's maybe increase that to 12, say. And then we've got 12 rectangles, and it says the area is 59.11. So that's much closer to that true value. And we could make that into 24. And now you can clearly see that those areas cut off are much smaller, and it's 62.87. So the more rectangles you use, the better the approximation. And this is a really key point for what we're going to be doing here.